In this video lecture, I will introduce the superposition theorem. The superposition theorem is an important theorem in electronics that's useful when a linear circuit contains more than one single source, a voltage or a current source. It is important to emphasize here the fact that this theorem can be applied only to linear circuits. We haven't introduced yet the concept of linear circuit. This will actually be the subject of a video lecture later on in this series. The superposition theorem is a derived result of the more general superposition principle that can be applied to any linear system, including, of course, linear circuits. The superposition theorem states that the response of a linear circuit, so the voltage between a pair of nodes or the current in a branch of that circuit, a linear circuit having more than one independent source, can be found as the algebraic sum of the responses to each independent source operated alone, where all the other independent sources are replaced by their internal impedances. By internal impedance of a source, we mean the series resistance in the case of a real voltage source and the parallel resistance in the case of a real current source. Let us start with a more conceptual example and consider a black box incorporating a linear circuit. Let us assume that this linear circuit has three independent sources, a real current source, a real voltage source, and an ideal voltage source. We represent here these sources as input sources to the circuit. Suppose we want to find the voltage between two given nodes of the circuit as a response to the three sources. We expose these two nodes, as we did for the sources, outside the black box. According to the superposition principle, in order to calculate or even measure, if we deal with a real circuit, the output voltage Vu, as we called it, we can proceed as follows. We first find the response to I1, the real input current source, alone. To do that, we need to switch off the voltage sources V2 and V3 and replace them with their internal resistance. This actually comes as a natural consequence of the fact that switching an ideal voltage source off means replacing it with a short circuit. So in the case of the voltage source V2, the internal resistance is R2, while in the case of the voltage source V3, the internal resistance is just 0. Let us call Vu1 the response of the circuit to I1 alone. We then repeat the same procedure, this time considering the response of the circuit to the voltage source V2 alone. As we did before, we need to switch off the other two sources, the current source I1 and the voltage source V3, and replace them with their internal resistance. As we know, when we switch a current source off, we get an open circuit. Let us call Vu2 the response of the circuit to V2 alone. Eventually, we will consider the response of the linear circuit to V3 alone. Again, to do that, we need to switch the other two sources, this time I1 and V2, off. Let us call VU3 the response of the circuit to V3 alone. The superposition theorem tells us that VU, the response of the linear circuit to the three input sources I1, V2, and V3, is equal to VU1, the response to I1 alone, plus VU2, the response to V2 alone, plus VU3, the response of the circuit to V3 alone. As an application example for the superposition theorem, let us consider a circuit including a resistor R1, a battery E, a current source I, and another resistor R2 in parallel with the current source I. And let us consider as the output variable for this circuit the voltage between nodes A and B. Let us call this voltage VAB. In this circuit, we have two independent sources, the voltage source E and the current source I, both ideal sources, which we can consider as the input variable for the circuit. By the way, this circuit, just including resistors and independent voltage sources, is a linear circuit. Again, we will discuss about the properties of linear circuits later on in one of the next video lectures. In order to calculate VAB in this circuit, we can apply the superposition theorem. We can start by considering the response of the circuit, which is the voltage between nodes A and B, as an effect of the voltage source E alone. In order to do that, we need to switch the current source I off. Once switched off, the current source is replaced by an open circuit. The circuit we have now is simply a voltage divider consisting of the voltage source E and of the resistors R1 and R2 in a series configuration. VAB is simply the voltage drop across the resistor R2. Therefore, we know that the voltage VAB as an effect of the voltage source E can be calculated as E times R2 divided by R1 plus R2. Let us now restore the current source I and consider the response of the circuit to the current source I alone. Before doing that, we need to switch off the voltage source E. When switched off, the voltage source is replaced by a short circuit. The circuit we get is a current divider consisting of the current source I and of the resistors R1 and R2 in parallel. The output voltage VAB is the voltage across R2 and R1 and the current source I. Therefore, the voltage VAB as an effect of the current source I can be calculated as minus I times R1 divided by R1 plus R2. The minus sign in the expression comes from the passive sign convention. Actually, the current I subdivides into two currents, I1 in R1 and I2 in R2, and in particular, I2 flows through R2 from the terminal at the lower potential to the terminal at the higher potential. Eventually, based on the superposition theorem, we can say that the voltage VAB, taken as the output variable of the circuit, can be written as VAB as an effect of E plus VAB as an effect of the current source I, which is given by E times R2 over R1 plus R2 minus I times R1 over R1 plus R2. For each of these circuits, find the voltage between nodes A and B as an effect of the current and voltage sources. In all of the circuits, E is equal to 1 volt and I is equal to 1 milliamps.